why Markman's theorem saves the Hodge conjecture for the A-type abelian fourfolds from Kontsevich's tropical counterexamples.
Thanks. Like I kind of said last time, the rest of my talk is kind of just about Hermitian forms. And so a lot of it is just about algebra. I mean, much of it is just about algebra. It's like an excuse to talk about algebra. So let's fix K equals Q root minus D, imaginary quadratic field. So yeah, I mean, there'll be some algebraic geometry in here, but while the error is clear, I just want to introduce some things that are just purely algebraic. So a Hermitian form on, let's say, a finite dimensional K vector space W is a map phi from W cross W to K, which is linear in the second variable. Because that's the way they seem to do it, and such that phi of xy is equal to f of phi of yx bar. Okay, there's that. So now the last ingredient of explaining Markman's theorem is really to say what the discriminant is. So I have to say two things before that. So phi is non-degenerate if like phi makes a isomorphism between W and W bar star. Phi is non-degenerate if phi from W to W bar star is an isomorphism. So phi okay, I want to say that, and let's write norm from K to Q. Let's let this denote the norm map. You know, the one that sends A plus B root minus D to A squared plus DB squared. Okay, then I'll tell you what the signature is. So suppose phi is non-degenerate. So there are kind of two ways to do this. Probably the quickest way to do it is, let's just say, pick a basis, W1 to Wn of W. And then you just set Cij equal to phi of Wi Wj. And then maybe there's a proposition. So the determinant that of Cij, that's in Q star. And it's like well-defined modulo, it's independent of the basis modulo the norms from K star. So its image in Q star mod the norms of K star is independent of the basis chosen. And let's just call the image the signature. So the image sig phi is called the signature. Phi. Okay, so then there's a couple of other things I want to explain. So one thing I want to explain is that when you pick a basis like this, you kind of have a complicated matrix. But in fact, you can just diagonalize Hermitian forms, and then the basis then the matrix we're taking the determinant of becomes diagonal. And because I'll use it, I'll just say something a little bit more general but that's also very elementary. A little bit more general than diagonalizing. So, maybe two forms. I don't know, phi on V, on W, and I don't know, psi on W prime are isometric if there is a K linear map, T from W to W prime, K linear isomorphism, respecting phi and phi prime. Phi and psi, that's bad notation. And then you can also take the perpendicular sum. So given, given phi, let me change the names of the vector spaces because I don't like those names. So given phi A, Hermitian form on A, and phi B on B, we get a new Hermitian form. Phi A perp phi B on A plus B, just by making A and B orthogonal. So just by setting phi A perp phi of B on sort of A1 B1 comma A2 B2 equal to kind of the obvious thing. So phi A of A1 A2 plus phi B on B1 B2. Okay, and then we can do, I think that's all I want. Now I want to say one little proposition. Maybe one more definition. So if A is contained in W and phi is a Hermitian form on W, you set a perp equal the set of all W and W, such that phi of AW is equal to 0 for all A and A. And here's a proposition. So suppose phi is a non-degenerate on W, and A contained in W is a K subspace. So let's assume phi restricted to A, which gives you another Hermitian form, is non-degenerate. So then W is isometric to A perp A perp. I'm not going to prove it because I think it's kind of probably well known and anyway easy to prove. But now using this, you can do a couple of things. So one thing that you can do immediately is to diagonalize Hermitian forms. So maybe just a little bit of notation for that. So given, I guess, C and Q star, let's write just parentheses C, and now like maybe bracket C, for the Hermitian form on K given by just phi of xy is equal to C of x bar y. And now, if you take a list, these guys are all in Q star. You set C1 up to Cn just equal to the perpendicular sum of all those guys. Okay, and then what you have another proposition, which is that you can always, if you have a non-degenerate Hermitian form, it's always isometric to something like that. So if phi is non-degenerate on W with W equals N, then phi is isometric. I don't know if I introduced this notation. Phi is isometric to C1 to Cn for some C1 to Cn in Q star. Okay, and that brings me to the next invariant that I want to, the next invariant I want to say, which is the signature of phi, which, I mean, we kind of already, you probably know what it is, because if I take phi and I base change it to C, so I think about it a Hermitian form on C, then you probably already know what the signature of that is. But another way to say it is the signature, so here's a proposition. Let's set A equal to the number, suppose phi equals. Suppose phi equals C1 up to Cn. Set A equal to just the number of I, such that Ci is bigger than 0. And set the signature of phi equal to just A n minus A. So then this thing is independent of which, it's an isometry invariant of phi. In other words, it doesn't depend on the choice of diagonalization of phi. It's just okay, and now here is, remember, everything I was saying here was worked out in much greater generality in like 100 to 150 years ago. And maybe one of the culminations of that much greater level of generality is this theorem of Landhair. Yeah?
Is the signature different than the signature you defined previously as some determinant? This is the old signature, the usual signature.
Oh, wait, did I say signature? Oh, no, did I? Oh, I don't want to call that the oh, crap, I screwed up. Oh, I screwed up. Yeah, the thing it should be called the discriminant. I just called it the signature instead of the discriminant. Maybe I didn't sleep for 1 hour last night. I woke up in the middle of the night. I didn't sleep. But everything that said signature before should be called discriminant. Discriminant, because the theorem, Markman's theorem is about discriminant 1. Right? Okay. Man, that was a bad mess up. Yeah. Yeah. But does it all make kind of sense now? Yeah. So yeah, the signature is this. That's the common word for the signature. I mean, you probably have seen, we've all seen this back in our school days. But I mean, we lived with this our whole life. And then the discriminant is the one thing that's a little bit like non-standard to think about a tiny bit. Because it's so the signature is a pair of non-negative integers adding up to the rank of the form. They call the dimension the rank. And the discriminant is that weird determinant, and it's an invariant of the Hermitian form, but only when you mod out by the norms coming from K star. I know. Damn. Okay, so now here's a theorem. So maybe before I write this theorem, so discriminant, I'll just write this. So, but it's also, and then discriminant of C1 up to Cn, that's kind of obviously just the product. Okay, that was a mess up. Okay, here's a theorem from the 30s, which is also proved in like far greater generality than what I'm stating. This is by this guy Landher. But then Landher's paper is like 3 pages long, and it proves everything completely, but it's actually really hard to read. And the other thing is that it's like really written in the old style, because it's like around mid-30s, around 35. It doesn't state the theorems. It just proves them, right? So there's no like theorem 1, theorem 2, none of that. There's just that whole 3 pages of stuff. It proves a lot of stuff. And in this case, what it proves is this: the signature and discriminant are the only invariants of non-degenerate Hermitian forms. Well, we only need this. I think he actually deals with degenerate ones too, but of non-degenerate Hermitian forms. Over K. So in fact, he doesn't work over an imaginary quadratic field. He works with much greater generality. Because of that, he has multiple discriminants and maybe multiple signatures. But the upshot for an imaginary quadratic field is this. Jacobson recovered all of his results, because Jacobson realized that you can, given a Hermitian form, he has this cool trick to produce a quadratic form. And then from Hasse or something, from classical things, he was able to recover this. I mean, they weren't classical then, but Jacobson's paper has the advantage of being kind of more readable. But that's a theorem. So, okay, so now back to the I think I have everything that I want from Hermitian forms. Okay. So now let's fix A, K, no, not A, K. Let's fix XK, Weil type, Abelian variety, Abelian 2n-fold, Do I want n 2n? I think I want 2n fold. 2n fold. And then let's fix omega. Let's set v equal to h1 of x cubed. And let's take omega, and that'll be from v cross v to k. No, not from v cross v to k. From v cross v to q of A-type polarization. And I looked up, I think maybe, who was that? Somebody asked me, I don't remember, like, what, yeah, Emre asked me, how do you know that you can get a V-type bipolarization by an ample vector bundle? And I looked up the answer. There's some messing around with the Riemann bilinear relations that I don't want to do that. But yeah, I mean, it's a theorem. The other thing is, like, for the general V-type abelian variety, the Picard, if n is bigger than 1, the Picard group is 1. So there's also that. Okay. So recall what this means. This means that omega, it means that omega, square root of minus d upper star of omega is equal to d times omega. Okay. So now, and then remember we make a Hermitian form on it. By this, so so you get Hermitian form. H from v cross v to k by setting h of xy equal to omega x square root of minus d lower star of y plus square root of minus d omega xy. Okay, and it's a cool thing, which I actually wrote. It's on my phone, but it's a cool thing to go and check that this actually gives you a Hermitian form. It's really totally actually fun, but I think I won't do it because it's fun. It's like one of those things that's fun to do in private, but probably not so fun to watch somebody do. So fun, and it's fun to check that this is a Hermitian form. Okay, and then what you get, there's a couple other things that I can say about it now that I have this, this notation. So really the main thing, I guess, is that Hermitian form H is non-degenerate. I think I already said that. And it has signature NN. So H is non-degenerate with signature n comma n. Okay. And now maybe I'll take this small time, because last time I said something about why all the things I'm saying to you are trivial. I'll just take a little bit more, because I don't think it was completely clear. I want it to be very clear that what I'm saying is trivial. So just take U. Let's take U of H. Okay, so that's an algebraic group over Q. An algebraic group over Q, whose base change to R is like UNN. Okay, and then that has a Chamorro variety, like basically associated to it. I mean, if you look, it's like, I guess more formally speaking, the Chamorro datum involves GU, but let's not worry about all that. Or PSU or something, but we won't worry, let's not really worry about that. Okay, so the Hermitian symmetric space associated to UH has zero-dimensional boundary components if and only if UH is quasi-split. So let me say it like this. Hermitian symmetric space associated to UH has zero-dimensional boundary components, rational boundary components. It always has zero-dimensional boundary components, zero-dimensional rational boundary components. If and only if UH is quasi-split, and that really happens if and only if H is isomorphic to 1 minus 1 raised to the n. But then you see by Landhair's theorem, that's really going to happen if and only if the signature is minus 1 to the n. It's not signature. I keep saying this. If and only if the discriminant of H is minus 1 to the n. And then what you just have to believe is having rational boundary components is the same as having maximal unipotent degeneration. So this is equivalent to having maximal unipotent degeneration. Of the Weil-type abelian varieties. But I'm not going to explain it in this way. I'll explain it in a longer way. I mean, I'm just really just for the experts. In fact, maybe it's a shorter way. Let's just explain it in a longer or shorter way. Let me just, here's my main observation. Another way to explain this is just to state this. Okay, here's my main observation. Okay, so suppose just k equals q square root of minus t. It's an imaginary quadratic field. And v is equal to k to the 2n. It's an even dimensional vector space. Okay, and H from V cross V to K, a Hermitian form. Non-degenerate Hermitian form. Okay, then the following are equivalent. And I'll prove this directly, or almost all of it, without talking about all this mumbo jumbo here. So one, there's a maximal isotropic subspace of V. So there's an n-dimensional k-linear subspace W contained in V. Basically consisting of isotropic vectors for, such that H of x, y is equal to 0 for all x, y, and W. 2, the discriminant of H is minus 1 to the n, and the signature of H, sig H is nn. And 3, there's a maximal unipotent degeneration, let's say pi from script x to delta, okay, of V type Abelian, whatever the dimension, Abelian varieties with Hermitian form, Abelian varieties with V-type polarization and where the Hermitian form is isometric to H. Hermitian form isometric to H. Okay, so maybe I think I've explained 1 and 2. I feel like I kind of beat those to death. There were 3, well, okay, let me just say, I'm going to use it, so I'll have to say what I mean, but let me just say in words what I mean. Delta is supposed to be a curve. The map x to delta is supposed to have a point called 0 in it. The map x to delta, it's supposed to be smooth on the complement of that point 0. And all the fibers over the complement of 0 should be V-type Abelian varieties. The whole thing should be polarized, and that polarization should give you a V-type polarization on all of them. Okay, so that's... Okay, so anyway, so the first part I used, let me prove it. I'm just going to prove it. So here's the 3 implies 1. Okay. There might be one thing that I'm supposed to say before 3 implies 1. But first, so suppose pi from x to delta, the maximal unipotent degeneration. So you write T for the image of the monodromy around that for the monodromy for T from H1. Actually, let's do this. Let's write S naught in delta minus 0. For some particular point, for some just randomly chosen point. For some randomly chosen point with the fiber smooth. Okay, the fiber of V-type Abelian variety. So just not 0. Okay, so then let's write V, set V equal to H1 of X of S naught. And then let's set T from V to V is a monodromy. So it's what you get when you go around that loop 0. Okay, and then let's take n is going to be the, maybe I want to say one thing. So it's a theorem of, that you can get from Schmid, but Van Gaiman told me it goes way, it's was known much before Schmid, that the, unfortunately, might be in a big problem here. Oh, good. Sorry. Okay. Yeah, let's write n is going to be the logarithm of the monodromy. Okay, and then it's a theorem that really, I mean, I know how to get it from Schmid's paper, but it probably goes back a long time before Schmid's paper, that n squared, the fact is that n squared is equal to 0. I mean, basically it's because the level of the Hodge structure is 1, so n squared has to be 0. And then, right. So suppose, So now what I want to do, I have to read the theorem that I'm trying to prove. So let's set W equal to the image of n. So let's set W equal to n of V. Okay, by assumption, maybe the other thing I didn't tell you is what maximal unipotent means. What maximal unipotent means is that n, the Jordan block of n is like as big as they can be. So that means, so by assumption, NV is half the dimension, of V. So since n squared equals 0, by assumption, the dimension of NV is 1/2 the dimension of V, because it basically means that we have to have like n Jordan blocks of size 2, which is equal to little n. Okay, now I'm going to prove that 1 holds, and it's kind of easy. So we have h of e to the n x. So the thing is, t preserves, so h of tx, ty is equal to h of e to the n x, e to the n y, and that's equal to h of xy plus h of nxy plus h of xny, since n squared is equal to 0. And that tells me that h of nxy plus h of xny is equal to 0 for all xy and v. Okay, so I don't want to erase what I'm trying to prove. So you get this cool thing, which is easy, but this is a cool thing that I'll write down. So h of nx ny, well, that's just equal to h of nx ny minus 0, but that's equal to h of nx ny plus this thing, plus h of nx ny plus h of xn squared y just by moving the n over here by, using the same formula. But that thing, this should be a minus. And then that's equal to h. That's equal to minus h of x n squared y. But that's equal to 0, again, because n squared is 0. So that means that 1 is proved. Okay, so now, so I have to do 1 implies 2. So for 1 implies 2, it's kind of similarly easy. Okay, suppose we have a isotropic space of dimension n. So we pick one element. We kind of work by induction. Pick one non-zero element of it. Since the, so I'm going to say it in words before I write anything, because otherwise I get confused. So pick one non-zero element of w. Let's call it like x. And then since the form is non-degenerate, you can find some y in V who's such that h of x, y is equal to 1, or h of x, y is equal to 1/2, or whatever thing is more convenient. Then you can make a two-dimensional vector space out of x and y, and you can find that that two-dimensional vector space, the Hermitian form restricted to it, is just the one with that's given by 1 minus 1. And then take the perp of that, and then go by induction. So here's my, you work by induction. I kind of wrote it in a fancy way that hopefully makes it work. I mean, not fancy, but to write U for the Hermitian space 1 minus 1. Okay. So like assuming 1, let's prove 2 by induction. Okay. On dim V. Okay. If dim V equals 0, there's nothing to prove. Otherwise, we take, so assuming dim V is not equal to 0, you pick x in V minus 0. Okay. And you find a y. And find y, such that h of, such that, you're actually in w minus 0. X in w minus 0. Okay, and you find a y in V such that h of x, y is equal to 1. You set A equal to span, so I guess I'll write it like this, kx plus ky. And then h restricted to A has matrix 0, 1, 1, something, h of y, y. And then the signature of that is 1, 1, and the discriminant is minus 1. So it has to be isometric to U. The signature of H restricted to A is 1, 1. The discriminant of H restricted to A is minus 1. So A is isometric to U. A is isometric to U. Okay, so and V is isometric. So maybe write isometric like this to A perp A perp. Okay, but then the signature of but then what you do is that W intersect A is only one dimensional. So W intersect this has to be n minus 1 dimensional. So W intersect A perp is n minus 1 dimensional. So the hypotheses still hold on A perp, and then you're done by induction. Maybe I should write that this is isometric to U perp A perp. So hypotheses of 1 still hold on A perp. So you're done by induction. And then the last thing is like 2 implies 3. So maybe notice, before I do 2 implies 3, which, I mean 3 implies 1. Before I say anything about 3 implies 1, let me first try to make it absolutely clear that this does what I said it does. So just without proving 3 implies 1, we know that if you have, from this, that if you have a maximal unipotent degeneration of A-type abelian varieties, with Hermitian form H, the discriminant has to be -1 to the n. And so now Markman proved the Hodge conjecture for abelian fourfolds of discriminant 1 for when the fourfolds are when n is 2. So you see that's -1 squared is 1, right? So that means that so this observation means that you cannot have a maximal unipotent degeneration of abelian fourfolds if the discriminant is not equal to 1. So this does what I said it was going to do. So for 2 implies 3, I mean, I'm actually just going to really just skip it because it's like kind of too easy. So for 2 implies 3, so just take, suppose E is an elliptic curve. Okay, then let's set A equal to just E squared, and just notice that let's set delta equal to 0D -1, 0, and the endomorphisms of E, which contains, I mean, if E could have Cm, in which case the endomorphism of E could be bigger than the 2x2 matrices on Z, but it's at least as big as the 2x2 matrices on Z. So actually, I guess I want to put it in here and contain it in there. So delta squared is equal to minus D. Okay. So what I want to claim, and I want to maybe write the details of this, but this thing makes A into a Weil-type abelian twofold. Oh, yeah, end A, yeah, sorry. So it makes A into a Weil-type abelian twofold. And A to the n into a Weil-type. If you just repeat this, then A to the n becomes a Weil-type abelian 2n-fold. And you can play around with this. It's a kind of fun thing to do, to see that you get a Weil-type polarization on it. And you have to kind of play with this because there's 2 factors, and there's a D and a -1, and they're doing 2 different things. But basically, you take the polarization on one, D times the polarization on one factor, and plus 1 times the polarization on another factor, and then that makes it a Weil-type polarization. And you can get the Weil-type abelian Hermitian form, and you can check the discriminant is always for this is -1. If I took it to the n, it would be -1 to the n. And they don't really care. Nothing really cares about the curve, so you could just degenerate the curve, and that gives you the maximal unipotent degeneration, and that's it. So, but I guess I'm trying to think of that. So that's how the proof. So maybe I can either can either stop here. Well, I'll tell you what, well, I mean, yeah, I think I told you this vaguely, but I'll tell you again, like I said, this thing should be part of like a bigger project with me and Helga Rudot and maybe possibly someone else. And what we want to do is really understand like why the Kontsevich's tropical Hodge conjecture, why disproving that would disprove the actual Hodge conjecture. And it seems to me that that involves understanding the relationship between the cycle class map in the algebraic setting and the cycle class map in the tropical setting. And that's what we're trying to do. I mean, in the tropical setting, the cycle class map involves some sort of polytopes in a real torus, and in the algebraic setting, it involves like Durham cohomology or some kind of cohomology. It's just like setting those things up is really what the project should be about, which is work in progress. So maybe, yeah, I think I stop here. I mean.